So our project is to explore the multiple object tracking on the mobile and edge hardware. The motivation is that nowadays the mobile device has much more powerful mobile processors. We have much more powerful CPU, and we have much more better TPU and NPU, because TPU and NPU are dedicated AI accelerators. And we also have the mobile modern AI models require greater computational resources. So the fundamental questions of our project is that can we enable high performance multiple object tracking with AI accelerators on modern mobile devices? MOT stands for multi-object tracking, is a real-time version task on video. It is based on object tracking, or object detection, and it handles occlusion and trajectory continuity. And ByTrack is a very classic algorithm for MOT. It follows the tracking by detection paradigm. It is lightweight and it has very high accuracy.
Yeah. So let me introduce you about our setup and architecture. Our architecture are two modes. This one is the local mode where everything, including the inference, the model, the processing, our tracking are all done on mobile device. And for the edge mode, we use mobile device only to capture the video and send these frames to the cloudlet, and cloudlet will do all the computation and send the results back. So the mobile device work or job in the edge mode are limited to only like capture the data and then display the results. So we did most of our experiments in Baker Hall at CMU. So like the network speed is fast and the bandwidth is large as well. And for the setup, detailed setup, we use two kinds of mobile phones. The first one is Google 7 Pro, which is the mobile phone we use for all the experiments in the following sections. And the Google Pixel 9 Pro phone is to use for the demo, which I'll show you later. And for the cloudlet, we use a cloudlet with NVIDIA GTX 1080 Ti, which is kind of like a powerful cloudlet. And for the object detection model, we use these models as the detection. So since multi-object tracking is a relatively complicated task, we split it into two stages. The first one is object detection, and the other one is the tracking. So the object detection detects the object, and the tracking layer tracks the detected objects. So for the detection layer, we also did some measurements. These measurements show that our MOT pipeline will be feasible and it is achievable. And also we have an estimate on how well and how fast will the MOT pipeline be in the future. So our conclusion are that in terms of the latency, the edge mode is faster, but the local mode is comparable. As for the accuracy, although there is a 7% drop in the MAP, it is acceptable because in real-world examples, the differences are small. Like, although there are 7% drop in MAP, there are only one missing and two mistakes, so it is totally acceptable. And for the MOT structure, let's walk.
Yeah, so for the MOT pipeline, first we have a camera which captures the video in 30 FPS, and each frame of the video will be put into a frame queue or frame sequence. Each time we only fetch one frame from the frame queue. The first step is to determine whether to drop this frame or keep this frame. And we actually use a flow control module here. The mechanism is that we drop frame when I is greater than 1, where I equals this complex equations, and we only keep one frame for every I frames. The purpose of this is to deal with the back pressure from the camera input and prevent the per frame latency from going indefinitely. In this equation, we actually combine the queue length and the end-to-end latency. The reason is that the user are free to choose different models or different frame ratio, and different setup will need to different end-to-end latency. So if we only depend on the queue length or the end-to-end latency, we cannot drop frame effectively. If we decide to keep this frame, we will then determine whether this frame is a key frame or not. In our project, we actually combine YOLO and optical flow for bounding box prediction. The reason is that the original ByTrack runs on a very powerful server. But in our case, we only have limited resources because we will run the ByTrack on mobile devices. Therefore, we just run YOLO on keyframes. YOLO is more accurate and can detect new objects, but it is slower. Then we will run the optic flow for intermediate frame. It is less accurate, but it's much more faster. Here, we also define a terms keyframe ratio. If we see the keyframe ratio to be 1/3, those red frame will be the keyframe, while those green frame will be the intermediate frame. Now, if the frame is a keyframe, we will run the neural object detection as we mentioned before. If it's not, we'll run the optic flow-based detection. Both of them will generate the bounding box with the same format, and there will be input to the tracking layer. In the tracking layer, we actually perform tracking on each frame. Because tracking requires very high FPS to avoid the ID switch caused by larger interframe movement. Here is the mechanism of the tracking. First, we have the person and its bounding box. And we make prediction for the next frame, where the person will be based on the person's previous motion. And now we have the new frame. With the bounding box, we do the IOU-based matching. And finally, we can see that this person is the same person as before. Finally, we will display the tracking results, including tracking ID and bounding box. This part is about our benchmark setup and benchmark results. So the task is to measure the MOT performance under different model keyframe ratio configurations on Pixel 7 Pro and cloudlet. We use the MOT 17-9-DPM dataset, and we have a bunch of metrics. The first figure shows the distribution of latency. Image 1 shows the H-mode latency distribution. As you can see, most of the mean of the latency is 70.5 milliseconds. The standard deviation is about 4.3 milliseconds, and P99 is 87.1 milliseconds. For the local mode, if the keyframe ratio is set to 1/1, the mean is slightly larger than before. It is 74.4 milliseconds, and standard deviation is 0.5 milliseconds. The reason for the large standard deviation in the H mode is that in H mode, we depends on the network, but network is mostly unstable, so the standard deviation is larger. In the third image, it is very interesting because for the first peak, it actually express those latency for the optic flow-based detection. For the second peak, it expresses latency for the neural object detection latency. This one is the breakdown of the latency. In the left side, we show the breakdown of the local mode latency. The blue bar basically occupy most of the end-to-end latency because blue bar shows the inference latency. And in the right side, we show the H-mode latency breakdown. The orange part, which is the network latency, occupy almost half the end-to-end latency. But based on the design for the token in Gabriel, the network latency can be hidden from the pipeline. In this big table, we show the multi-related metrics. For the first part, we show the multi-related metrics for H mode, and with larger model, we basically have larger multi, and we have much more mostly tracked objects. For the local mode, the main tendency is that if we set the keyframe ratio lower, we actually decrease the multi. And this is the overall results for this three graph. The key takeaway from this graph is that first, H mode delivers high accuracy at the same FPS, and higher FPS at the same accuracy, while local mode remains comparable. Second, optic flow significantly boosts FPS with only a moderate reduction in accuracy. So to answer our questions before, yes, AI accelerators make accurate mobile MOT a reality.
So let me show you a demo of our project. This screen shows the live demo of the tracking of person. As you can see here, people are tracked with different colors of box, and but you may like to move more intensively to show its effects. Like, yeah, you can see Sijie is being tracked. And that's all. Thank you.